Okay, let's get started. So we had the exam on Friday. We're in the middle of grading it. The plan is to have it all graded, and we will return it to you on Friday, and we'll spend most of the first hour on Friday going over the exam, okay? There was a new homework assignment posted on Friday for those of you who didn't see it. Here it is, and it'll be due this coming Friday. And the idea here is to go through the discussion of beta decay today and on Wednesday, which will basically cover all the material you need for that particular homework assignment. And then after this, we'll go on to alpha decay, and then we'll start a discussion of nuclear reactions. Okay, I have another brain teaser for you. This one will take a while, so I'm going to give it to you today, and I want you to think about it. And I was told this was an interview question that Bill Gates used to use at Microsoft. I don't know if it's true, but that's what I was told. Okay, so there's an evil prince and 7 dwarves. And the evil prince arrests these 7 dwarfs and puts them in a dungeon overnight. And what he tells them is that the next morning he's going to line them up in order from the tallest to the shortest in such a way that each one can see all the ones in front of him, but he can't see the ones behind him. And the evil prince is going to put a hat on each of these dwarfs' heads. The hat will be either green or red. And he will ask each dwarf in order what the color of the hat on his head is. If they get it right, they're free, they're released. If they get it wrong, they're killed. Okay? So this is all explained to them, and they're put in the dungeon overnight. And the question is, what is it, if anything, these dwarfs can do? They can talk to each other during the night. What is it they can do to maximize the number of them that will survive the next day? Okay? So they can talk to each other all night, but the next morning they're going to be lined up, and each one is going to get to say one word, which is either green or red, and that's it. So think about it, and we'll talk a little more on Wednesday about how many will survive and what the strategy is. The answer is a little bit surprising, but we'll get to that on Friday. Okay. So, beta decay. Back on day 1, we talked about the fact that there are 3 kinds of radioactive decay: alpha, beta, gamma. We've talked a little bit about the kinematics of alpha decay, and we had a lengthy discussion over last week about gamma decay, and now we're going to go on to beta decay. And beta decay in some ways is the most complicated of all 3 kinds of radioactive decay. And it illustrates a lot of the issues we've already talked about. So beta decay is obviously a spontaneous form of radioactive decay. It involves a situation where a nucleus has either too many neutrons or too many protons to be sitting at the bottom of one of those mass parabolas. And so in what's shown here, you have a parent nucleus, Z and A, and through this process of beta decay, it's transformed into a nucleus with either one more or one fewer protons, and obviously a corresponding change in the number of neutrons, so that the A remains the same. Okay? And depending on whether it's a neutron turning into a proton or a proton turning into a neutron, you get either an electron, a negatively charged electron emitted, or a positively charged electron emitted, a positron. Now, when radioactivity was first discovered, this was around the turn of the 20th century, people were firmly convinced that energy and momentum and all those things were conserved. And when they looked at alpha decay, they saw something like this. So in alpha decay, remember, you have a parent nucleus which spits out a helium-4 nucleus and has the Z and A lowered, the Z by 2 units and the A by 4 units. And if you measure the energy of the alphas that come out in alpha decay, they are in discrete peaks, that is discrete energies, and the maximum energy you've calculated corresponds to the difference in rest mass energy between the parent and the daughter nucleus. Okay? So when people started studying beta decay, they thought if they measured the energy of these electrons that were emitted, they would see something similar to that. That is, discrete lines that correspond to the difference in energy between the parent and daughter states. Okay? So this is an example of one of the early beta decay studies that was done. This happens to be the decay of bismuth-210 into polonium-210. And what's being plotted here is the energy spectrum of the beta-minus particles, the electrons, that were observed to emerge from bismuth-210 decay to polonium. And what you see looks incredibly different, totally different than what you see in alpha decay. Namely, what you see is a continuous spectrum that goes from 0 energy up to the maximum energy allowed by this decay. So Q beta is the difference in rest mass energy between the parent and daughter, just like Q alpha was that for the alpha decay. But now you see this continuous energy spectrum. This was really a puzzle, okay? Because what it seemed to imply was that somehow energy was being lost, okay? If you had an electron emitted with an energy down here, that's a lot less than the Q value. Where did the rest of the energy go, okay? And people began to think, well, maybe energy isn't conserved in this process. Maybe nuclear processes are really different than what we've seen in classical mechanics before. And so they began to do more sophisticated experiments, and eventually they figured out a way to image these decays, that is, visualize what was actually happening. And they used devices called cloud chambers, where you have a mist, usually it's of alcohol, and when a charged particle like an electron goes through it, it produces ionization, and along the track you get little droplets of the alcohol condensing, and you see a track. Okay? So they did an experiment with a beta decay. This happens to be a beta decay of a nucleus called helium-6, and this is a cloud chamber image of one of these decays. In the helium-6 decay, a neutron turns into a proton and converts the helium-6 into a lithium-6. And in this image up here, right up at the top there where the two tracks emerge, there was a helium-6 nucleus initially at rest. Okay? And it underwent one of these beta decays. And in these experiments, a magnetic field was applied to bend the tracks of electrons. So this curved track you see going over here is that of an electron. And the straight, very short track, the little blob you see coming off to the left there, is the track of the daughter lithium-6 nucleus. So this is a real problem, because now you've got a situation where the helium-6 was initially at rest, meaning its momentum was 0. You've got an electron that's going off down and to the right. You've got a lithium-6 going down and to the left. You can clearly see that the momentum vectors of those two things cannot possibly add up to 0. There's an imbalance of momentum there, because clearly there's momentum going down and there's no corresponding momentum going up. So not only did energy appear not to be conserved, so did linear momentum. And then it gets even worse, because it turns out the angular momentum of helium-6 in its ground state is 0. It's an even nucleus, okay? Lithium-6, it turns out, has a ground state spin of 1, and the electron we know has a spin of 1/2. So there's no way to add together 1/2 and 1 to get 0. So it looks like angular momentum is not conserved either. So this was really a problem. And this persisted until about 1930, when Wolfgang Pauli came along and said, no, angular momentum, linear momentum, energy are absolutely conserved. We're not going to give that up. And he made what in those days was considered to be a very radical hypothesis, which is that there's another particle emitted here that you don't see. Okay? And he originally called it the neutron, but then another particle got dubbed the neutron. The particle which Pauli suggested has come to be known as the neutrino. Okay? And it solves all these problems. Okay? And so this is Pauli, about the time he suggested this. And the idea was, okay, this particle doesn't leave a track. We didn't see a third track coming out of that image, and the thing that produces tracks are charged particles. So this neutrino, if it actually exists, can't have any electric charge. Furthermore, when we measure energies, we don't see it. So it must interact weakly, and weakly's put in quotes there because he didn't know exactly how weakly. Because of the fact that this beta spectrum, which I showed you a minute ago, goes essentially up to the total Q value allowed for the decay, that means the neutrino can't have very much, if any, mass. If it had any mass, as we'll see in a minute, it would have shifted the spectrum down from the endpoint. So it can't have much, if any, mass, but it has to carry both energy and linear momentum in order to conserve energy and momentum. And furthermore, in order to make the angular momentum work out properly, he hypothesized it has to have spin of 1/2. And so the idea was that in this process of beta decay, both an electron and a neutrino are created, and they share the decay energy and the momentum. So the explanation for that continuous energy spectrum in the bismuth decay is that here's our bismuth 210, A neutron turns into a proton. It spits out an electron and an object we call the electron antineutrino. And these two guys emerge. This is the one you see the track of. You don't see this. But they share the energy and the momentum. Okay? So in 1930, that was a radical idea. People didn't like the idea of new particles. There are only two of them known at that point, the electron and proton. A couple years later, the neutron was discovered. But it took a long time for the neutrino to be accepted as a real particle. And the problem is that it's incredibly hard to detect these things. I think, as I mentioned earlier, they literally can travel through a light year of lead without interacting, so it's tough to see them. And it took nearly 30 years before they were detected in the laboratory and confirmed to be real objects. In the 1950s, so in the late 50s actually, Fred Reines and Cowan were the first people to actually detect a neutrino. And the source of neutrinos that they used was actually a nuclear reactor. And we'll spend a fair bit of time later on talking about that. In the beta decay process, which is what happens with most of the fission products that are produced in a reactor, the object that gets created in the beta decay is this thing we call the electron antineutrino. And what Reines and Cowan realized is you can detect them by allowing them to interact with a proton and kind of doing an inverse beta decay. So an electron antineutrino can be captured by a proton and turn the proton into a neutron, and in order to conserve electric charge, a positron gets emitted. And so they brought a detector, which was essentially a large tank of liquid scintillator, an organic liquid that has lots of hydrogen in it, and it has the property that when radiation hits it, light is given off. And they brought it near the reactor and measured the number of neutrons and positrons that were created. They detected both of them in it, and they were able to show that they saw more of these events when the detector was near the reactor or when the reactor was on than when it was off. And so they were the first people to confirm that this hypothesis of Pauli's was actually correct, namely that neutrinos really are produced in the process of beta decay. It turns out this same reaction is now being used to monitor nuclear reactors. And we'll talk about that a little bit later once we go through the discussion of fission. And it's an idea which has caught the attention of the International Atomic Energy Agency, because not only can you measure the power level of the reactor, it turns out you can learn something about the nature of the fuel which is undergoing the fission reaction as a result of looking at the of the neutrinos that come out. So this was the first confirmation. In the early 90s, Fred Reines got the Nobel Prize in Physics for that measurement. Okay? So neutrinos really do exist, and now it turns out you can actually use them. Now, I was trying to be careful and point out that this thing is called the antineutrino. Clear what was going on, and so a collaborator of theirs, Raymond Davis, did another experiment where he took a big tank of dry cleaning fluid, which contains chlorine-37, and again he brought it near a reactor, and he looked for a slightly different kind of reaction. He looked for a reaction particle to convert chlorine-37 into argon-37. And notice the difference here. Here we're turning a proton into a neutron, and this object that came out of the reactors was able to do that. In this reaction, you're actually converting a neutron into a proton. And what Davis was able to show is that this particle, this thing that came out of the reactors, can't cause that reaction to happen. And so there's a difference between the object that comes out of the reactors, this thing we call the antineutrino, and the particle we now call the neutrino, as demonstrated by those two reactions not both occurring. So nowadays, we can use accelerators to produce neutrinos and do experiments with them. And this is an experiment that was actually done, but there's similar experiments done outside of Chicago at the Fermi National Accelerator. And in all of them, the same process is used. You take a very large accelerator, and you accelerate a proton beam to as high an energy as you possibly can, and you smash it into a target. And you allow all the debris that comes out of that to get filtered through a mile of rock and dirt. And at the other end of that mile of rock and dirt, you build your... And so what's called a bubble chamber. It's similar to the cloud chamber, except it's filled with a liquid, usually liquid hydrogen or liquid neon. And again, the idea is that charged particles produce tracks in these things, which you can see. So there's a camera looking down into this thing, and a mile in that direction is the accelerator. And what happens occasionally is a neutrino comes in and interacts and produces a spray of tracks. So you see the neutrino coming in here, right? No, you don't. You don't see the neutrino coming in, okay? Because it doesn't have any electric charge. It doesn't produce a track. But at this point, all of a sudden, you see a spray of particles coming out. So something happened there. And the interpretation of this image is that this was a neutrino that was produced in the accelerator that traveled through that mile of rock and dirt and got there and then interacted with the nucleus here and produced all these particles, okay? Now, you're going to ask me, well, how in the world do you actually know that's a neutrino? And the honest-to-God answer is you don't. What the people who do this for a living will tell you is they see more events like that when the accelerator is on than off, okay? And if you don't like that, then you're not going to like anything about neutrinos, because that's as good as it gets in neutrino physics. Okay, there is no way to actually say for sure that was a neutrino coming in. You study lots of these things, and eventually you convince yourself that something is going on when the accelerator is on that doesn't happen when it's off. Okay, so you're saying this is an engineering class. Why in the heck should I care about neutrinos? Well, I've tried to motivate it with the idea you can actually use them to monitor reactors, but there are other reasons to care too. And we've talked a little bit about the idea that inside the neutrons and protons there are these objects called quarks running around. And I think I probably said that it turns out there are 6 different kinds of quarks now. The two that you need to explain the neutron and proton are what are called the up and down quarks. But then there are heavier versions called strange and charm, and still heavier ones called bottom and top. Okay? And we think that's all there are, but you're going to tell us for sure when you do the research. And they seem to come in families of 2. They're grouped together in pairs because of their masses and because of the way they decay. And what we've discovered over the years is that there are 3 kinds of leptons, 3 versions of the electron. So there's the electron, and then there's its heavier cousin called the muon, which for all intents and purposes looks like an object that's just 200 times heavier than the electron, except a muon knows it's not an electron. There's something else inside it that distinguishes it from being an electron other than its mass. And then there's a heavier version still called the tau, which weighs about twice the mass of a proton. And associated with each one of these leptons is a corresponding neutrino. So there's an object that is a neutrino that is somehow correlated with the electron. There's a different one associated with the muon, and there's a different one still associated with the tau. And that distinction is what we call flavor. So there are 6 different flavors of quarks. There seem to be 3 different flavors of leptons that are correlated with the quarks in this way. Again, who cares? Well, it turns out in the Big Bang, every particle that ever was or ever will be was created. And for those that are stable, they're still around today. So neutrinos were produced in enormous numbers in the Big Bang. And if you go through the arithmetic, it turns out there are about 100 per cubic centimeter of each of these types everywhere in the universe today, left over from the Big Bang. So every little cubic centimeter has 100 of these things flying around. And that's a lot of neutrinos. They have a finite mass. We've discovered that now. And it turns out that if each of them had a mass of about 5 electron volts, that is 1/100,000th as much mass as that of the electron, then if you added up all the mass of the neutrinos, it would close the universe, meaning it would stop the expansion and make it collapse on itself. Okay? So these little tiny things that you think don't matter could be the most important whole thing in the entire universe. Okay? It turns out it's not true. We now know that's not true, but for a while it was believed that. So how do you learn about neutrino masses? Well, one way is to study beta decay. Because of the fact that the neutrino and that electron are going to share the decay energy. So here's another beta decay spectrum. So this is the energy that the beta particle, the electron, carries, and that's the number of them. And what I tried to show is this blue curve is the continuous distribution you would get if the neutrino had exactly 0 rest mass energy. And what would happen then is the electron could have any energy from 0 all the way up to the full energy allowed by whichever decay you were looking at. But given the fact that we believe firmly that energy is conserved, if the neutrino has a finite rest, then that means when we create the neutrino, that costs a certain amount of energy, E equals mc squared. And so this energy spectrum of the electrons would then be shifted down by an amount equal to the mass of the neutrino times c squared. So what people have done for 50 years now is to look very, very carefully at these beta decay spectra and look for evidence of the spectrum stopping a little bit sooner than it should if the neutrino were massless. And the most studied system is tritium. We've talked about tritium before. This is a heavy isotope of hydrogen. So one of these neutrons turns into a proton and converts the tritium into helium-3. In the process, an electron is created and an electron antineutrino. The total decay energy for this process is only 18.6 keV. It's a very low energy, as we'll see, for beta decay. And from studying this spectrum very carefully, people have concluded that the neutrino, if it does have any mass, must be less than about 2 electron volts. So very, very small, not 0. And there's a new experiment that will be done in the next few years, which is going to have sensitivity a factor of 10 lower than this. And so if the neutrino mass is as much as 0.2 eV, then it will be seen in that experiment. You're going to get sick about neutrinos, but I like them, and it turns out they are interesting for engineering these days, so I'm going to spend a little bit more time on it than you might think. They have some very peculiar properties, other than the fact that they interact very weakly. And one of them has to do with what we call handedness, or helicity. So the object that we call the neutrino is what we call left-handed. And let me explain what I mean by that. So this object, the neutrino, let's say it's created with a momentum vector pointing to the right. Okay, so there's a process that creates a neutrino and it travels from your left to your right. It turns out that object will have its spin. Remember, it has a spin 1/2. And that spin can only have 2 projections along any axis. The axis of interest to be the axis in which the momentum vector is pointing. The spin of that thing we call the neutrino is always pointed in the opposite direction. So the momentum's that way and the spin vector is pointing the other way. You can think of that as being a left-handed corkscrew. If you think about how it would have to be spinning, that's a left-handed corkscrew. The object we call the antineutrino has the opposite helicity. So when it's created and it travels from left to right, its momentum's going that way, its spin vector is pointed in the same direction. Okay? And this helicity quantity is defined in this complicated way. It's the dot product between the spin and momentum vectors divided by the magnitude of that dot product. And for neutrinos, that quantity is -1. For antineutrinos, it's +1. So the neutrino is called a left-handed object, and an antineutrino is called a right-handed object. Experimentally, there are ways to tell this, and that's how we know that this is in fact true. The beta particles, the electrons and the positrons that are created in beta decay, also have a helicity. Their spin vectors are not randomly oriented with respect to their velocity or momentum vectors. One of the distinctions between the electrons and neutrinos for this argument is, in this case, the neutrino mass is considered to be exactly 0, whereas we know the electrons and positrons have a non-zero rest mass. And so the electrons and positrons can't be moving at the speed of light, whereas if the neutrino mass were really exactly at the speed of light, the fact that the neutrino has a tiny, it's almost moving at the speed of light, but not quite. So the helicity of the beta minus particles, the electrons, created in beta decay is equal to minus divided by the speed of light. The closer they're moving to the speed of light, the more like a neutrino they behave. Okay? And similarly for the positrons, their helicity is plus V over C, and so the faster they move, the more they look like an antineutrino in terms of this spin momentum correlation vector. Okay, enough about neutrinos for a minute, but we'll come back to them later. So one of the additional complications of beta decay is there are 3 varieties of it. And we've actually talked about them a little bit already, but we're going to spend more time on that now. So beta minus decay is the situation where essentially a neutron inside a nucleus converts into a proton. And in order to conserve energy, momentum, and angular momentum, an electron and this thing we call the electron antineutrino are emitted. And the example shown here is the one I showed you earlier, which is bismuth-210 turning into polonium-210. So we start out with 127 neutrons. One of those neutrons becomes a proton. So 83 protons become 84, and 127 neutrons becomes 126. Okay? That's beta minus decay. And that happens for nuclei which have an excess of neutrons, too many neutrons for the number of protons that they have in their nuclei. Okay? A corresponding kind of decay which happens for nuclei that have too many protons for the number of neutrons is positron emission. Okay? And the example shown here is sodium-22, 11 and 11. You think, well, that doesn't seem like too many protons, but it is. This nucleus would prefer to have more neutrons than protons. So one of these protons turns into a neutron, so 11 protons becomes 10, 11 neutrons becomes 12, and you convert sodium into neon in that process. And again, in order to conserve energy and momentum and electric charge, we have to emit a positively charged object, because here we had 11 positive charges, and now we've only got 10. And electric charge, as far as we can tell, is absolutely conserved. So there's the antiparticle, the electron, the positron emitted. Again, in order to conserve all the other numbers, a thing we call the electron neutrino has to be emitted. And so what's really going on in this process is a proton's turning into a neutron, a positron, and a neutrino. Now remember, we've got fully dressed atoms, meaning we've got a nucleus and the same number of electrons orbiting as there are protons in the nucleus. And so another process can happen which accomplishes the same thing as positron emission. Namely, it converts a proton into a neutron, but it doesn't produce a positron in the end. This is known as electron capture. Okay? And so you can think of it essentially as rewriting this equation. If I take this positron from over here and drag it over to the other side of the arrow, it turns out whenever you do that, you convert the particle into its antiparticle by bringing it across the arrow. So the positron becomes an electron, and this electron is one of the bound atomic electrons which was there in the sodium-22 atom before the decay happened. And it turns out that electron occasionally spends some time inside the nucleus, and while it's there, it can be captured by one of the protons there. This is analogous to what we talked about last week in terms of internal conversion, where you had an excited nuclear state which transferred its energy to an atomic electron. Well, here it's not just transferring energy, it's actually absorbing it. So a proton and an electron combine and produce a neutron, and then in order to conserve energy and momentum and angular momentum, a neutrino is emitted. So in both the positron emission and the electron capture, the same thing happens. Sodium-22 turns into neon-22. In this case, you get a real positron emitted. In this case, you don't. Okay? Yes? Positron capture. Where would the positron come from? We don't have positrons sitting around in atoms. But it's a good question. So you could do something analogous. You could take a positron that you produce somewhere and you shoot it at a nucleus. You tell me what the reaction would be. Suppose I have a positron plus some nucleus Z and A. What's going to happen? What would it interact with in the nucleus? The neutron, right, okay? So it would interact with the neutron, and what would it produce? A proton. And let's see, this would be an antineutrino. Yes, that happens, okay? It's a weak interaction. The cross-section of the probability for that will be very small, but in principle, yes, that can happen. It's just that we don't normally have positrons sitting around atoms like we do in a neutral atom here. We've got electrons. Well, you're absolutely right. Other questions about that? Yes? We're going to talk about that. It depends very much on the energy available for the decay, the Z of the nucleus, a whole bunch of different factors, but we're going to talk about that. Yeah, hang on just a second. In general, if positron emission can occur, then electron capture can also occur, and both will occur at some level. But it isn't always true that both processes happen, as we're going to see in a minute. There are certain situations where only this can happen and not that. Okay. And to get to that discussion, we have to go through this slightly tedious process of looking at the energy release in beta decay and accounting for the electron masses. Okay. So let's first talk about beta minus decay. And so we have a situation where we have a nucleus Z and N, which turns into Z plus 1 and N minus 1 and spits out an electron antineutrino. And we now want to calculate the beta decay Q value, the energy release in that process. And just like any other process, and you want to calculate a Q value, you take the masses and you multiply by C squared. Okay? And that's the definition of a Q value. And I'm going to do things a little bit differently than we've talked about before. Initially, I'm going to look at the nuclear masses. Okay? And remember, I said you can always use either nuclear masses or atomic masses, and as long as you're consistent, you will get the correct answer, and that's true. So I take my initial nuclear mass, I subtract from that the sum of the masses of all the things that are produced, I multiply that by C squared, and I say that's the Q value. Okay? And if I look at that, that's the nuclear mass of Mr. X minus the nuclear mass of Mr. Y minus the mass of an electron, because I created an electron in that process, and the mass of the neutrino, all times C squared. Okay? Now, from experiments that have been done now, we know the neutrino does have a finite mass, but it's less than about 0.055 electron volts over C squared. And for everything we're going to do in this class, that's good enough to be 0. So we're going to neglect the mass of the neutrino in everything we talk about from now on. Okay. So this is how I would calculate the Q value if I were talking about nuclear masses. Now I'm going to switch to atomic masses for a minute. Okay? So remember, in an atomic case, you've got the nucleus plus the electrons that are bound to it. And so if you think in detail, that means the atomic mass of species X is equal to the nuclear mass of that species, the same thing I was talking about over here, plus Z times the mass of an electron. Because in the neutral atom, I've got Z electrons as well as Z protons and N neutrons. And these electrons are bound by some amount of energy. Okay? When they are captured by the nucleus, X-rays are emitted. So it then requires energy to liberate those electrons from the atom. That's called binding energy, and that's a negative quantity. So the atomic mass of species X is the nuclear mass plus E times the electron mass minus the sum of all the electron binding energies. Okay? Similarly, for species Y, the atomic mass of Y is the nuclear mass of Y plus Z plus 1 times the mass of the electron, because remember, there's Z plus 1 protons in species Y, minus all the binding energies of those Z plus 1 electrons. And we said before, we can calculate the Q value by either taking the difference in nuclear masses or the difference in atomic masses. Okay? So the Q beta value, Q beta minus, I calculate this way. It's the initial atomic mass, okay, it's just rewriting what I had a minute ago, minus the final atomic mass, minus the mass of that one extra electron I created. And the point of going through this is to show you that the electron masses cancel out. Okay, so I've got in my initial state Z electrons. In my final state, I've got Z plus 1 minus 1. And so I have Z minus Z plus 1, or sorry, minus a minus Z plus 1, plus M sub E. The electron masses all cancel out. Okay? So the Q beta value is then just the difference in atomic mass of species X minus the atomic mass of species Y, plus this term, which is the difference in the electron binding energies. And normally, that's a very small number. The difference in the atomic electron binding energies between an element Z and an element Z plus 1 is usually very small, and normally we neglect that. There are a few cases where you have to worry about it when the Q value for the beta decay is very, very low. But we're not going to worry about it in this class. And so the bottom line is, to calculate Q beta minus values, it's extremely simple. It's simply the difference in atomic masses between the parent and daughter. The electron mass And that's a reason for using atomic masses in these calculations. Okay? So you go to the back of Lilly's book, you look up what he calls the mass defect, and you take the difference between the mass defect of the parent and that of the daughter and multiply it by c squared, and that's the Q value. Okay, so use atomic masses and your life will be simpler. Where does that energy go? So the reason these things decay is because this Q value is positive. Energy is released in the process. Well, the energy gets shared between the electron and the neutrino that's emitted. And the neutrino we're assuming is massless, so that means its kinetic energy is its total energy. In the case of the electron, it isn't true because the electron has a finite rest mass. So some of the energy goes into creating the mass of the electron. The maximum kinetic energy the electron can have, however, is equal to the maximum energy the neutrino can have, and that's equal to the Q value for the decay. Because ordinarily, the electron and neutrino share the energy, but it could be, just by chance, that the electron ends up with all the energy and therefore the neutrino ends up with 0, or vice versa. So that's why that endpoint, or that spectrum of the electrons from the beta decay went all the way up to the endpoint. What corresponded to the endpoint is when the neutrino got 0 energy. Okay? And in all of this, we're neglecting the fact that the nucleus actually recoils a little bit, because remember I showed you that image of the helium-6 decay. There was a track from that recoiling lithium-6. The kinetic energy of that big, heavy nuclear recoil is very small in general compared to the electron or neutrino energies, and normally we neglect that. Okay, it's a small correction. Okay, so that's beta minus decay. In beta plus decay, you go through exactly the same logic of looking at the nuclear masses and then using atomic masses. And what you find in the positron decay, and I would encourage you to go through this because it's not immediately obvious, that in the positron decay, the Q value is the difference between the initial and final atomic masses minus twice the rest mass energy of the electron. Positron emission can only occur if you have an energy difference between the parent and daughter atoms that's greater than twice the rest mass energy of the electron. If that isn't the case, it can't positron decay. Okay? Whereas electron capture, which is the corresponding process, can happen regardless of what the Q value is, because you don't have to create that positron. And so when you go through the same algebra, and again I encourage you to do it, for electron capture, this is the process. The Q value for electron capture is the difference between the initial and final atomic masses minus, and now you do have to account for this, the fact that the electron was bound when it was captured. A certain amount of energy was already given up when that electron got captured, and you have to account for that. So the more tightly bound the electron is, the lower the Q value for the electron capture will be. And these are numbers you can look up online or in the back of the table of isotopes. Okay, so these are the ways you calculate the Q values for the 3 different decays. So beta plus decay can only happen if the Q value is greater than twice the rest mass energy of the electron, meaning greater than 1.022 MeV. If it's less than that, then only electron capture can occur. If it's greater than that, as you were asking before, both processes happen, and in a little bit we'll see how you calculate the relative amounts of positron decay versus electron capture. So just a question, in electron capture, what radiation is emitted? Neutrino, right. Ordinarily that, and one other thing would be emitted. So this is the process. Neutrinos are hard to detect. So how is it in the laboratory we detect electron capture? Pardon? I'm sorry, I can't hear you. If it goes to an excited state, yes, very good. It would be a gamma ray. But suppose it's a ground state to ground state electron capture. What else would be emitted besides a neutrino? Another electron? Why would another electron be emitted? It might, but why? Well, we're capturing an atomic electron, and usually the electron that gets captured captured is one of the innermost electrons that's spending more time in the nucleus than the outer ones. And so if you capture that electron, you create a vacancy in an inner atomic orbital. That's a very highly excited atomic state. And that vacancy in that orbital will get filled by another electron falling in, and an X-ray will get emitted. And so you get characteristic X-rays of the daughter atom emitted, and that's usually the signature for electron capture, okay, because of this atomic process. Okay. In the case of alpha decay, which we haven't gone through in detail yet, but I think I talked about this a little bit, we imagined that the alpha particle existed inside the nucleus before the decay happened, and it was a quantum mechanical tunneling process that let it get out. That isn't the case here, okay? And we've already discussed this, that if you took an electron and tried to confine it inside the volume of a nucleus, the uncertainty principle would make it have such a high energy that it's much higher than the beta decay energies we observe. So we couldn't have an electron sitting there before the decay happened. What goes on in beta decay is the electron and the neutrino are created in the process of the decay. Just like the photon wasn't there before state gamma decays, the electron and neutrino weren't there before the beta decay happened. And the way we picture this is not in one step. What we imagine is that a virtual process happens first, one of these cheating the universe out of some energy for a short period of time. So for example, in the neutron beta minus decay, we imagine that what's happening is a neutron spontaneously converts into a proton and one of the carriers of the weak force, the so-called W particle. And make electric charge be conserved, it has to be a negatively charged W. That W exists, but its mass is something like 80 GeV. And so in a beta decay where you have 1 MeV available, that can't happen really. So it's a virtual process that is allowed only by the uncertainty principle. And almost instantly, the W converts itself into an electron and an antineutrino, and that's what emerges. Okay? And similarly, for the positron decay, what goes on is a proton turns virtually into a neutron and a W+, which immediately decays into a positron and a neutrino. Okay, so that's how we imagine beta decays really occurring. You can't observe this intermediate step, though, because of the uncertainty principle. So what you see is that and then the final state, or that and then the final state. Okay. And what beta decay does is allow nuclei to move down these mass parabolas we talked about earlier. So you've seen this kind of thing before, but now you can understand a little bit more what's going on. So if we take an odd A mass chain, 125 for example, and we plot all the nuclei that have A equals 125 and just distinguish them by the number of protons in the nucleus. So these nuclei over here have more neutrons than they should, and these nuclei over here have more protons than they should. And you say, well, what do you mean than they should? Meaning relative to the nucleus which has the lowest rest mass energy for that A, which turns out to be tellurium-125 in this case. And so these nuclei can move down this mass parabola by converting neutrons into protons, and they do that through the process of beta minus decay, whereas the ones over here can move down the mass parabola by converting protons into neutrons, and if they have more than 1.022 MeV available to them, they will positron decay, otherwise they will electron capture decay. And similarly for the even A nuclei, remember there are two mass parabolas, one for the even evens, which is lower, and one for the odd odds, which is higher because of that pairing energy. And so the beta decays will actually move you from one mass parabola to the other. So if you start out on the odd-odd and do a beta minus decay, you'll move to the even-even and then back and forth. And again, over here, these are neutron. Yes, that label goes here. Sorry. These are neutron rich, so these are beta minus decaying. These are neutron deficient, so these are positron and electron capture decaying. Okay. Now, the Q values for these decays range all over the map. If you look at the known nuclei, the lowest known Q value for beta decay is about 2 keV, and the highest is about 20 MeV. Okay? The typical sort of Q value is around 1 MeV. So if someone asked you, what's a typical beta decay energy, an MeV is a good answer. As we're going to see in a minute, the Q values largely determine the half-lives for beta decay. And because of this relatively large range of Q values, it turns out the half-lives vary enormously. The shortest half-life known for beta decay is about 10 milliseconds, and the longest known is about 10 to the 16th years. Okay, so again, an enormous range of half-lives, partly to do with the Q values and partly to do with the angular momentum that the electron and neutrino have to carry away. Okay. This is going to get a little messy, and I don't expect you to know the details, but I want to try to motivate some of the phenomenology we're going to use later to classify beta decays. And so this is a very quick quantum mechanical treatment of beta decay. And if you go back to the discussion we had in the second week, I think, on quantum mechanics, I wrote down this formula called Fermi's golden rule, which is the way to calculate the rate for any process in quantum mechanics. And so this transition rate, which now is going to be beta, but originally it was just a general expression, is some constants, 2 pi over h bar, times a quantity called the square of the nuclear matrix element, VFI. And this is an operator that you sandwich between the initial and final wave functions that describe your system, times something we call the density of states, the number of quantum mechanical final states that are available to the system. Okay? So this VFI is some operator that we're not going to define very well. Okay? Basically, it's something that converts a neutron into a proton or a proton into a neutron. I have some initial wave function describing my parent nuclear state, and I have some final wave function describing the daughter nuclear state, and this operator connects the two. So if I could do that integral, I would be able to calculate this matrix element. So my initial state is just my nucleus. Here's my operator, I call it O. The final state, though, has 3 particles in it. So I've got my final nucleus, that's this guy, but I've also got an electron and a neutrino, and I have to keep track of all these things to do these calculations. Okay? Now, in the decay, the electron and the neutrino that come out are basically free particles. So I can describe the wave functions of the electron and neutrino in the same terms we used in the first week. So I can write down an expression for the wave function of the electron as a function of distance or position. It's 1 over some volume. Define some volume in which we're doing these calculations. And then it's essentially sines and cosines, but I prefer to write it as e to the I p dot r over h bar. But you could write it in terms of sines and cosines also. And here, p is meant to be the momentum of the electron. And similarly for the neutrino, I can write the wave function of the neutrino 1 over this same volume, e to the I q dot r, where q is now the momentum that the neutrino is carrying away. Okay? Now, I warned you early on that there are cases where we have to use relativistic kinematics as opposed to classical mechanics, and this is an example of that. Okay? So we're talking about electrons, and we're talking about beta decays where the energies are on the order of an MeV, and so the criteria for where you have to use relativistic mechanics is when you have a kinetic energy that's on the same order as the rest mass energy of the particle you're. And the rest mass energy of the electron is only half an MeV. So we've got a kinetic energy which could be greater than the rest mass energy. We're forced to use relativistic kinematics to describe both the electron and the neutrino. Okay? So the energy of each of these particles, whether it be the electron or neutrino, I've got to write as the square root of p squared c squared plus m squared c to the 4th. And the kinetic energy is the difference between the total energy and the rest mass energy. Okay? So the total energy includes the rest mass energy. And this kinetic energy is what I've been saying is on the order of an MeV in beta decay. So if I have an electron that has a kinetic energy of 1 MeV, its total energy is therefore 1.511 MeV, the sum of the kinetic plus the rest mass. And the momentum I can calculate from that formula, just plugging in this number. It turns out to be 1.4 MeV over c. Why do I do that? If I then take that and try to calculate p over h bar, because remember that's the thing which enters into my exponential here. And again, I play my usual trick. I multiply top and bottom by c, because I can't remember what h bar is. But I remember what h bar c is. So 1.4 MeV, h bar c is 197 MeV femtometers. So p over h bar is 0.007 per femtometer. Okay? Now we're talking about beta decay happening inside an atomic nucleus. Okay, the size of the atomic nucleus is a few femtometers. So R is going to be on the order of a few femtometers. When I multiply it by P, a very, very small number. Okay, and so if I do my Taylor series expansion of this exponential, I would get 1 plus an initial term that goes as P dot R, but P dot R is going to be very, very small, and I'm going to neglect it in this kind of calculation. So for all intents and purposes, these complicated exponentials can be approximated to a very accurate extent as just being 1. They're just constants. Okay? Now, as I said before, to do the calculation, you have to assume this is all happening inside a certain volume. The volume, it cancels out in the end, but to do the calculation, you define some volume V. So you imagine this is happening in a box of volume V. And in the back of Lily's book, he goes through this calculation of how you find the total number of final states, the density of final states that the electron or the neutrino can occupy. And so the density of states for the electron is 4 momentum squared dp times the volume divided by h bar cubed. And similarly for the neutrino, you get a similar calculation. So you take these values for the density of states and you plug it back into Fermi's golden rule, and you get this messy expression. And again, I don't want you to worry about the details. I'm just trying to motivate why beta decay spectra they do. So this decay rate has some constants out front, another constant which is a measure of the strength of the weak interaction, the thing that's making this all happen. Here's our nuclear matrix element, which will matter in the end. Some more constants, and then these products of the momentum squared and momentum squared of the electron and neutrino. And this matrix element, again, is just the operator that connects the initial and final state integrated over the wave function. And what we're trying to do is just find the shape of beta decay spectra. Okay. I think I'm going to stop right here because it's a little bit involved. On Wednesday, we'll finish up this discussion, show why the beta spectra have to do, and then we'll go more specific nuclear decays. Okay, so I'll see you on Wednesday.